let's gather ourselves. I think one dude needs to gather himself more than anybody, so come along with that dude, please. Whew. Just, let's, with our eyes closed, just sit up in your chair. Maybe try to pull away from the back of the chair so that it's really just you supporting you. It helps keep the attention as well. Just settling in and noticing our bodies. Noticing the sounds in the room. Noticing your visual field. Letting your gaze be wide. With that soft gaze, just looking into the space behind your eyelids. No strain, just a relaxed gaze. Just like laying on your back and looking up into the sky on a summer day. Notice how there is something to see there. Just gently bring them all back together. Good. Okay, I'm better. I'm better. I'm here with you. Does anyone have any questions on the homework assignment? Problems? Actually have the notes. Anything you want to talk about in that assignment? Anybody blank pens over here? No. That's where I buy my own pens. That's why I buy them by the case. Yes, ma'am.
Okay, for B of 1, 2, 3,
Okay.
can I arbitrarily choose an A sub n that contains 1, or do I have to do something using powers? Like, could I go like A, n, or, so like A sub n is n to the 0, n to the 1, n to the 2. Does that make sense?
So no, you can't
I
pick
didn't think so.
specific A's.
Okay.
So let's take a look at, both these. What did you do for A on 1, 2, 3?
I just talked about the example that we talked about in class, like, because
Yeah.
it's always going to be contained backwards.
Yeah. So, let me actually retract what I said. It depends on which direction you're trying to go with that problem, Kayla. So if you think that that statement is false, then a counterexample is absolutely in order. Is that the route you were going?
No, I think I was trying to make sure that I was trying to make sure I explored all of the options before I made a choice.
Gotcha. So, and maybe let's talk about it. And maybe what you were saying is actually, maybe I just totally misunderstood what you were saying notation-wise. But let's see, here's 1, 2, 3. Yeah, for part A, the tip is, we did talk about
Yes.
something like this in class, the archetype. So good thinking on that. And then in B, we've got these subsets of the reals that are nested, and that goes on infinitely. But we do know that they are finite, so A sub k is finite and non-empty. So what you literally could do here is write out an arbitrary A, and I would start with maybe A sub 1, right? Because these are going to be contained in that. As soon as you define A sub 1, you're set. So A sub 1 must look something like this, and maybe that is what you said.
Yeah.
Is that something roughly like what you were doing?
Yeah.
And I just misunderstood your.
Yours is better.
Well, it's not a bad place to start, for
Yeah.
sure. And so at this point, this has to be the case. I don't know what the A's are, except that they are real numbers. And now that I've got this nesting, I own every set in this chain in some way. I don't own them exactly. I don't know what their precise nature is in terms of elements. But this containment tells me something big. So what are we supposed to see here? Oh, the intersection is finite and non-empty. So true or false, the intersection is finite and non-empty. So there's really two things to argue here. They're both similar arguments, but subtly different for sure. First off, the finitude of this intersection. How did you feel like you came up with a decent argument for that?
No. I got really confused.
Okay, Noah, did you come up with something?
Well, I said that the intersection had to be a subset of A, so it couldn't, A1, which is finite, so it couldn't be infinite. It might be empty with that argument, but it's definitely not infinite.
That's cool. So Noah's yeah, exactly. So Noah's hitting on the key here, and the key is this: that if I have two sets A and B, their intersection diminishes the sets. And in fact, I could say this, or that intersection has to be contained in both of those. You can't make a set bigger with intersection. You can only make it smaller or stay the same. So this is really the key here. And Noah's argument is right on for the finitude, indeed. So what about non-emptiness? That one's a little trickier, but it's, be prepared to write sentences, right? You're gonna have to explain things. Sometimes it's gonna be that'll be the painful part of some of these things. Like, how do I express this idea that seems obvious in some way? What is the key here? What is the key to knowing this must be true? And what would it mean for this intersection to be empty? Let's maybe come at it from the other side. If this were an empty intersection, what would that mean? This is a good tea time. Man, I'm already like healed just being here with you guys. Just talking, it was like all it took was an empty set. I'm good to go.
There's no one element that's in all of them?
Yeah. So there's no particular one of these that is in all of them. Yeah, why would that be a problem?
They're all subsets.
Yeah.
Those are all subsets, right? And so right now, hopefully you're starting to see like, okay, this kind of makes sense. The struggle will be putting that into an argument that makes sense. So there's a little bit of a struggle here, but push that struggle. I'll be kind. I'll be very kind. Just give it a shot. Kayla, does that help on this one?
Yeah, thank you.
You're so welcome. Any other questions, friends? it's crazy. I feel so damn good being with you guys. Like I have a rush of adrenaline. I feel euphoric. Does anybody watch Euphoria? The HBO, the horrible HBO show, teen drama. Oh man, yeah, it's a good show. It's horrible. Yeah, really horrible. I don't have that kind of euphoria. I haven't like dosed with anything this morning, except real analysis. That's what I'm high on. It's enough. Okay, well let's cruise on, and let's see. I think this isn't due till like next Friday or something. So when we come, I will have online office hours tomorrow, and I will have online office hours on Friday as well. And I will send you the links. They're going to be Zoomy things. I'll make sure you get those in case you want to talk. But otherwise, next Wednesday should be I hope it's hopping with questions. Okay, cool. And feel free to always email me if you're just like, am I doing this right? I'd be delighted to help you out. Okay, we are talking about kind of another one of our big tools for the semester, but it's also a really heavy concept. And it's kind of what makes real analysis work, and it's what makes the real numbers what they are. And that's, could I be more vague? Probably. But I want to talk today about the axiom of completeness. And hopefully you read 1-3. Oh no. And I won't ask you. But, oh, you don't have your book. And I didn't put up 1-3. Son of a. Would you shoot me an email, please? And just remind me of that. I'll get that up. Michael, sir, what's the axiom of completeness?
For any bounded subset of the real numbers, there exists a lowest upper bound.
Damn close, but it's also true. Actually, you gave a different version of the axiom of completeness than we have. So let's talk it up here. Michael's damn close there. So every non-empty subset A of the reals that is bounded above has a least upper bound. There's a lot in this sentence. A lot. So every non-empty subset of the reals bounded above has a least upper bound. What does bounded above mean? Trinity, what does bounded above mean? Be more precise. You're right. Can we be precise? Can you help me write a mathematical definition? So here, let's write it out. So A subset of R is bounded, and I use BDD for my bounded, above if it's okay, it's all right. So let's draw a picture. Let's help you work it through. So you were saying something. What was the original thing you said?
It has, like, there's an upper limit to it.
There's an upper limit. So if this is A is made up of all sorts of stuff. Just make it look kind of weird here. If this is A. When you say there's an upper limit, what do you mean?
Well, I think I remember it being something like all of the elements of A are less than that certain ground.
That's it. That's good. So let's pull that back. So there is this thing. There is, and that was really the first thing you said. There is. So there exists some right-hand point, and the set lives to the left of that point. So that's bounded above. So if there exists an M that's a real number, such that A is less than or equal to M for everything in A. Just, and that, you did say that. I was just like wanting to get that into a analytic definition. So that's beautiful. So that's bounded above. So it doesn't run off to infinity, essentially. Yes.
Is that S2?
Such that, yes, thank you. Yeah, please, all questions, yes. That is my such that. A lot of folks in here are used to my hieroglyphics, so please, I'm ready to translate it any moment. Okay. So now we know, so we have a non-empty subset that is bounded above, it has a least upper bound. Now it gets a little tricky. What does that mean, Noah? What is a least upper bound?
It means it's an upper bound that is less than or equal to all other upper bounds.
Ooh, that was very clean. I like that. That's a pretty definition. Yeah. So let's formalize that. And Noah totally nailed it there. So S, we use S for a very good reason. We'll get to in just a minute. Is a least upper bound, BD, and you can abbreviate that love if you want. We're gonna end up throwing away that term because we have a cooler term anyway for it, is a least upper bound for A, set A, if, and then there's really two things. First off, S is an upper bound, and Noah had this all lovely, lovely woven together. So if S is an upper bound, we know what that means. And then if B is any upper bound for A, and let's draw a picture here. Oh, here, we'll come back over here. So looking at this, I could have called this upper bound S, but clearly there are better choices. I could have gotten a lot tighter. So here's another upper bound. The least upper bound kind of looks like it would just go right through that point right there. And so what Noah was expressing is that the least upper bound is the one that is less than or equal to any other upper bound. It is the least of all the upper bounds. So if B is any upper bound for A, then S must be less than or equal to that B. Beautiful. So that's a really good, that's an important definition. What is the lovely term for the least upper bound? Why is it S simple?
I don't know how to say the word.
Supremo, there we go, yeah. Just like the pizza almost, right?
Yeah,
Like,
yeah.
you know, so S is equal to soup, and this is how we literally say it, the soup of A. So that's how that is pronounced, like officially in the math world, standing for the supremum of A. So make a little note. That's how you say that word. Okay, so let's see here. Oh, let's get the other one while we're at it. What's the flip side of all this? So take a moment on your paper. What is the definition of bounded below? See if you can just do that on your own, like come up with the mathy definition without looking up here. See if you can just come up with it. What is the companion for least upper bound for lower bounds? So now if we're thinking about lower bounds, what is the flip side of soup? I gotta run, enough stumbling, I gotta run to the restroom. So I'll be right back. take a look, see what's going on. Yeah, beautiful. Beauty, beauty. Yeah, outstanding. Yeah, then that's definitely. Can you come up with that?
Sure.
Yeah. Still thinking? Cool. Okay, awesome. Good, good, good. How you doing now? Yeah, you're looking, that's looking solid.
Yeah, I'm just confident.
That's how school works.
Exactly what I did.
Exactly, and that's a smart plan. Oh, that's great. My goodness, I need spectacles to see that. You have incredible eyesight.
I'm not rude.
I mean, I need to go to your optometrist, is what I mean. Okay. Kayla,
Yeah.
would you help me out here, friend? Let's kind of come together. So a set of the reals is bounded below if, and I don't want to force letters on you. So what is the definition going to be here?
A is bounded below if there exists some n and r, such that for every a, or such that every a is greater than or equal to n for every a. in
Yeah,
N.
beautiful. Yeah, definitely. So there is a number to the left of the set. Perfect. Beautiful. Thank you. Did you end up finishing up the?
Almost. I mean, I could put it together.
Okay, let's put it together. Okay,
Okay.
so
So.
what did you call this thing?
I call it L.
Oh, I'm sorry, the name for it.
Oh,
Like
the greatest lower bound.
GLB, thank you, is a greatest lower bound, GLB, or A if, okay. Did you use S, or what did you use, L?
I used L
I like that.
for low.
I'll ask you about your letter in a minute, Michael, because I'm gonna use the different letters, so go ahead, my friend.
L is a lower bound, and,
Yes.
for some Q,
Oh,
which is also a lower bound,
so Q, okay.
L is greater than or equal to Q.
So Q is another lower bound for A. And what was the relationship here?
L is greater than or equal to Q.
Beautiful. It's the rightmost upper bound that I could possibly get. Yeah, that's lovely. Michael, what letter did you use?
I,
And why?
because of the fancy word.
That's it. Do you want to try saying it?
Infima.
Oh, man, that's good.
Oh.
That's it. Are you like a Latin?
I just watched a couple videos on it.
Oh, man. Oh, that's super exciting to hear. So we would call this L the nth of A, and that stands for, as Michael correctly pronounced, infima. Lovely. Okay. Let's find some of these things. So now we got some computational problems to mess with, and this will be fun. I'm going to give you a set, and I want you to, so a little caveat, if the set is not bounded above, there is no supremum. You could say it's infinity, but we just say there isn't one. So subtlety here. There's a thing called the reals, which of course you know about, but then there's also a thing called the extended reals, and that is the reals union this this thing called infinity. And we pretend like that's a thing that we can access. We're not going to. But that is a way to proceed. union on infinity and then have that be a thing. You could say the supremum is infinity if the set was unbounded. We're just going to say there is no supremum. So let me get rid of that real quick. So here's the problem. Find sups and imps. Set one. Oh, okay. I think I got a little too excited with these. Let's start out a little chiller. A little less insane. So let's take the set of all x such that x is between 0 and 1, or, and then let's just union this with the point 2. When you can in this class, sketch things out. You're going to be so much happier. It's so much easier on your brain. Again, we're starting out chill. We'll build up speed. These things look crazy. I've written down here. Lots of ways to draw these things. Just use one kind of retro style. Does this look good for what this set is all about? Cool. If you've already got that one, we'll come back to it. I'll pop the next one up for you. So plus 2 is 3 minus negative 1 to the n plus 1 over n. N is a natural number. Let's just let everybody have a chance to at least get something they feel good about for the first time. Can we check in on one here? Anybody care to regale us with the tale of infant soup? What do you think, Al?
Soup S1 is 2, inf S1 is 0.
I like it. Soup of S1 is 2. And the inf of S1 is 0. One way to think about this, once you have a picture, if you're having trouble visualizing what's happening, for a soup, if you can get a decent picture, and sometimes this would be misleading, but just approach from the right and look for the stopping point. As soon as you spill into the set, you've gone too far. Now, in this case, the soup is actually in the set. That's totally cool. 2 is an upper bound for this set. Anything else couldn't be. If you'd said 1.5 is an upper bound, you'd be lying, because 2's to the right. So any number inside here is going to fail. 2 is the leftist you can go. Notice that, like I said, 2 is in the set, so it's not just a supremum, it's a maximum. So I'm going to make a little note here. A maximum is a supremum that is in the set. Similarly, for a minimum being an infimum that's in the set. So we have a fancier term. This is like calculus. We're much fancier. We're way fancier than calculus in this class. And then here, if I come in from the left, I can actually get to 0 the minute I move to the right of 0. I've got stuff to my left. So you might say to yourself, wait, if here's 0, couldn't 0.00001, couldn't that be a lower bound? No. Why, Michael?
Because there's always a real that's closer to 0 that isn't that one you get.
Exactly. Take half that number. It's to the left. So you can always, no matter how tiny that little spot is, you can always spill to the left. We're going to come up with a nice theorem that's going to make this easier to argue. But for right now, is anyone needing clarification on any of this? You're good? Okay, awesome. Let's draw this out together. This is fun. This is where this thing started getting exciting. This would have been the first one. It was good to warm up just a touch. So one thing that might help is to actually enumerate this set, to kind of just list it out. So when n equals 1, I'm going to do it slowly here, right? So I'm going to get 3 minus -1 squared over 1, 3 minus -1 when n is 2, cubed over 2. Let's do one more just till we get the rhythm. So I'm enumerating that, and then I'm going to simplify. So this is going to be 3 minus 1, so 2. This is going to be 3 plus a half. So let's just say 3.5. Yeah. I already regret decimals. I hate stupid decimals. What a mess. So I don't want to write 3.5 either, like I'm like in 3rd grade. So I'm going to write 7 halves. And then this is, oh shit, sorry. And then this is going to be 3 minus 1/3, so 8/3? Yeah, thank you. Okay. Yes, a fellow snorter. I am also a snorter. So then we could keep doing these computations, but let's actually understand the mechanics behind the production of this set. So it looks like I'm anchoring at 3. So 3 is somehow integral to this set. And then I'm bouncing back and forth, starting to the left. We could actually kind of change that definition. We could have put a plus here and knock that power down by 1. But I was apparently trying to be clever or tricky or something. So we take 3 and then we move 1 unit to the left, and then we move a half unit to the right, then a 1/3 to the left, then a 1/4 to the right. And so we're seesawing back and forth, decreasing each time. So the first set is going to be 3, and then we go minus what was it, just -1, right? So that gets me to 2. And then I'm going to plus a half. And that gets me to 7 halves. 3 itself is not actually in this set. And then I'm going to go minus a third, plus a fourth. Ooh, that's nice on the right. That'll be all the nice even things, right? Fourth, oh, plus a fourth. Okay. Writing's getting a little sloppy there. Is that still clear what I'm trying to indicate? It's like a pendulum dying out, right? As we move forth with some asymmetry to its motion. So, my set looks like this. Trinity, what is the soup for this set?
7 half.
Yeah, how about in my infimum?
2.
2, beautiful. So notice how once I've got the set drawn out, it's actually pretty obvious what the infinite soup are. And in fact, they're minimum and maximum because I literally can attain them. So here for this set, we have the soup. S2 is 7 halves. The infimum of S2 is 2. And note that this is a max and this is a min. Any questions on that, friends? Sounds good. All right, let's boot this up another level. Oh, let's go right to this one. Okay. S3. S3 is equal to all things of the form 1 over m minus 1 over n, where m and n are natural numbers. Supernth, please. This one might take a little while. There's 2 moving parts here. One tip might be to fix one of the parts and work from there and see what happens. Yeah, that's smart. That's smart. Okay, so these numbers. So look at the set. I agree with you if those were free range.
So I
Chicken
have to
numbers,
erase my
whatever.
first one because I thought that was a 10 set.
Yeah, you can only get down to 1, I think. Good, good. How's it going, Anna?
I'm trying to somehow like make one smaller than the other or just keep.
Yeah, and so like I would even start a little simpler. What's the smallest number in that set? One. So maybe look like M be one, and then think about what happens with all the possibilities of this, right? So it's gonna be one minus, what are the possibilities for this thing here? What can one over M be? Yeah, exactly, or even just one half, 1/4, right? So it's gonna be all those nice kind of harmonic numbers like that. So then you're gonna have one minus all of those, that's part of the set. And then let M be two, and think about what, yeah, so it's like kind of a more methodical approach, does that make sense?
Yeah.
Yeah, yeah.
Alright, thank you.
You're welcome. And you know, honestly, a little grid couldn't hurt for thinking about this. You could literally do M, and then you could do N like this to organize the data and make a matrix. Not the worst idea. If you want to gain a sense of what's going on, it's in terms of organizing your thought process. That's all. I'll actually stay. Okay. Yeah, right? Let me go across this way here. No, I should probably keep going. It's going to be two, 1/2. Oh, so this is 1/2 minus, so 0. Lot. 3/10. Yeah, something like that. And then what do we got? 1/3 minus 1, so negative 2/3. 1/3 minus 6. Oh, right, okay, so we'll have that beautiful. Ooh, it's looking pretty. Just kind of a nice, like, so see, just looking at this is even starting to give me some kind of insights into owning the entire set, because I'm noticing, first off, there's gonna be this beautiful zeros, which I could have caught, you know, up front, but maybe I wouldn't have if I hadn't organized things. And so then this, I'll bet this is negative 3/4. Let's check that out. So, yep. And this is gonna be negative 4/5. And this is gonna be negative 1/4. This is gonna be and so forth. I think so. Is that right? No, that doesn't look right. Oh.
It's the one you didn't want to do.
Yes, it's the one I didn't want to do. Oh, lazy man. Down. Okay, cool. I think I see what's going on here now. Do you think you got it? Do you think you kind of got a grip on it? Yeah, let me take a look. Yeah. That's it. let's talk it through. I'm sorry, I know some of you are still working, but definitely want to make sure to do a few more things here. Do you have, so like do you have contenders for your soups and ifs? Is everybody kinda? Yeah? So let's argue it through. First off, the most this 1 over m can be is 1. And then I'm just subtracting stuff off, always, right? So literally, 1 has to be an upper bound for this set. Does that make sense? That 1 is absolutely the ultimate upper bound. Likewise, the least this can be is -1. And then I add little positive, sprinkles onto it. The sprinkles get tinier and tinier. So the least anything in that set could be is -1. Those aren't in the set though, right? Those points are not in the set. But look at what's happening on this top row in this leftmost column. I'm taking 1 and I'm subtracting a quantity that is headed to 0 as n gets larger and larger. So I'm taking 1 minus something that's shrinking. I'm approaching 1, and you can see that right down here. So we see these points clustering toward 1. Not getting there, but clustering toward. In fact, I'm going to put a nice open circle here just to indicate that. And then on the flip side, I've got -1 plus smaller and smaller things. So I've got this sequence of points here approaching -1 from the right-hand side. So it doesn't really matter what's happening inside. There's all sorts of shit going on in the middle. Soups and imps aren't about the middle, right? We're mostly concerned about the extremes. So this would, if you started trying to plot this out, you would probably be unhappy. Unless you're really into that kind of thing, then you might be really happy. But what I'm mostly concerned about are the leftmost and rightmost edges. So all the stuff in the middle, irrelevant. So what could we say here? Trinity, you came up with it. What did you get for the soup?
It's just 1.
1. And then what was your imp?
-1.
-1. Does this sound reasonable? But we don't have a way to prove it right now. It's kind of like right now it feels a little nebulous, right? It's like, oh, we're guessing, and then we just said it, so it must be true. Even though it feels right. We don't do that shit, right? That ain't math. We're going to demonstrate it, but we don't quite have the tool yet. So that's why we need theorem. Which theorem is it? Theorem, whoop. It's like 138. Yes, lemma 138. And lemma 138 says the following. We're going to prove this because it's kind of a neat proof. This will be one of your main tools this semester. So you're going to want to be referring occasionally. By lemma 138, I know that this is the case. So let's get the exact statement up here. Let S be an upper bound for a set A. Then the supremum is S if and only if for all epsilon greater than 0, there exists an element of the set A that is to the right of S minus epsilon. And with this theorem, it definitely helps to draw a picture of what's happening, especially for this part, because this looks really weird. So let's think about it. If this is my supremum S right here, and I'm not going to put a point on it, because it might not be in the set. So I gotta be really careful with these pictures. S may or may not be in the set, but I know it's as close as I can get from the right without spilling into the set. Or at least into the midst of the set, having stuff to the right. So look at what this says. If that's the supremum, for any positive jump to the left, there's a positive, so subtract off epsilon, and there's S minus epsilon. No matter how tiny that jump is to the left, and epsilon is positive, that's why it's important for that, there's gotta be some part of the set that's inside that gap. No matter how much, I breathe on it, just tiny little wafer thin blowing of to the left, and suddenly I'm in the set, there's stuff to the right. That's what it means to be the supremum. It's a sensitive condition. It's almost unstable in some ways to the left. We want to even introduce an idea of stability. So let's do a proof here. And we got two directions. So let's go this direction first. So S is the suit. And let's indicate to our reader that we're going to go to the right. So let S equal the suit of A. Maybe we can even think this through together. One direction we can definitely do. The other direction's a little trickier because you got to do this. You got to make it. It's a trick. And if you don't do the trick, it can be very painful. So let's let S equal the suit of A. I got this picture going up right over there. And let's let an epsilon be greater than 0. So now I'm going to consider S minus epsilon. And I want to argue that there has to be some element of A to its right. So let's actually write this as a question. Why must there be an element of A to the right of S minus epsilon? See if you can come up in your head, like think this through, answer that question. Another way to phrase that is, why is S minus epsilon not an upper bound on the set? That's another way to say it. Ashley, okay, got the sh sounds in my sad little addled brain. Ashley, do you have a sense of what's up here? That's, when you say small, what do you mean? That's okay, we're here to talk and like figure it out. That's okay, okay, cool. What about upper bound? So what does it mean to be the least upper bound? Why couldn't this be an upper bound for the set? So let's talk this through together. So how does this relate to this quantity in terms of like equal, less than, or greater than? It's less than, right? Because epsilon is positive. Nice. Yeah, absolutely. So we've already said S is the supremum. And let's take a look together. You might, oh, you don't have your book. So let me refresh our memory of definition 132. So definition 132 says, you're the soup, or S is the soup, and let's put that right up here. Definition 132. So we say S equals the soup of A. That means two separate things. So first off, S is an upper bound. And two, that if B is any upper bound for the set, in other words, it lives to the right of everything in the set, then it has to be to the right of S. So this definition 132 is plain now. It's really the only thing we have to work with, because we're trying to come up with a new definition for soup, and that's the only one we got. So Ashley, now, why can't this be an upper bound? Looking at that definition, because S is the least upper bound, why can't this be an upper bound? Yeah, because if this is another upper bound, it has to be to the right of S, or equal to S, right? So this thing right here tells me. So this means, and this is because epsilon is positive, that's happening. This implies that S minus epsilon can't be an upper bound by definition 132 part 2. So since it's not an upper bound, there has to be something to the right of it. A can't live to its left. So since S minus epsilon is not an upper bound for A, there is some element A that lives to the right. And I like writing it like this. The book does it backwards, but I like this because it's more suggestive in our minds of right and leftness. And so that's actually what we have right here. We just proved that direction. Any questions on it? Does that make sense, Ashley? Like how that argued out? No, do you have questions?
No, I think that makes sense.
Okay, cool. All right, now let's go the other direction. But Ashley has paid the price for us all. I'm going to help on this one. Because there's a freaking trick. So now we're going to assume this condition holds true. Assume. First off, we have two things. We know that S is an upper bound, right? That's like the meta assumption. And for all epsilon greater than 0, there always exists an element of A to the right of S minus epsilon. Okay, so we want to show, let's actually put this up here. We want to show S is the soup of A. We only have one way to do it still. Definition 132 is our only tool right now. So let's put that note here. Must use definition 132. So let's see, there's two parts to it. What do we have so far? So we have to show those two things.
Well, we know S is upper bound.
Woo, yeah, right? So like, woo, got it. So, so definition 132 part one is given. Love it. Yay. Now we gotta show part two. So what is part two? Part two almost gives us the trick, right? Kayla, you're nodding your head. So like, what should I assume here?
If there's some b to the right.
Yeah, yeah,
Or
or
we just
or
have
just
to
that
find-
another open
yeah.
bound, right? So we're gonna pick another upper bound and show that it must be the case that this holds true. Okay, so for part two, we let B be another upper bound. A now what we want to show is that B has to be to the right. So let's just do some contradiction stuff here and assume that B isn't to the right of S. And assume that B is actually less than S. And we're going to show this leads to a contradiction. Show this can't happen. And herein lies the trick. And if you read the proof, you probably know the trick, you might remember it. But since I have this quantity, I'm going to subtract B from each side. So S minus B is now a positive quantity. What are we working with? We're assuming this. For any positive quantity, if I leap that much to the left, part of the set lives to my right. So, using star, and let's call this star, let epsilon equal S minus B. We are assuming this is true. So by star, there exists some element A in A that lives to the right of S minus epsilon. Now I'm writing it backwards, just like I said I would, but I just did it. So sorry. But what is epsilon? Let's plug. Chug here. I.e., A is greater than S minus B. Because that's what I'm letting epsilon be. It's supposed to be true no matter what. I've got a positive one. I.e., A is greater than B. Where's the contradiction? I just produced an element in the set that is to the right of B. What is that contradiction? Kayla, what is that contradicting?
Then that would mean that S is inside of the set.
Let's go back a little more primally. Remember, you gave me this.
Oh, sure, sorry, B is inside of the set.
Yeah, yes.
Which would thus not be an upper bound.
That's pretty poor behavior for an upper bound.
Yeah.
Right? So we had assumed B was an upper bound. Kayla gave us that. That shows B can't be an upper bound. So this contradicts the assumption that B is an upper bound for A. Thus, this can't happen because having that thing be positive was the cause of all our sufferings. So if B is another upper bound for A, B has to be greater than or equal to S. And I'm going to even write here must be greater than or equal to S. And that is part 2 of the definition. We picked another upper bound and showed that that condition must hold true if that starred condition holds true. So by definition of 132, S is equal to the soup of A. Done. Oh God, our time goes so fast. Last minute, let's just take our last minute together. Can you, right now in these last few minutes, come up with a theorem, a lemma 138 for infimums? What would that look like? So a lemma 138 companion for infimums. Anna, you got an idea on how to roll with this?
Not really. I was trying to think back from the last one, like why must there be an element to the left?
Yeah, let's think it through together. This is good. You know, once I call you, you're not off the hook, right? So it's like we're gonna either hang out, you either got it or we're gonna hang out and get it. So let's look at the, try to just flip this thing. So the first thing they assume here is that S is an upper bound on the set. What should we assume instead?
I is a lower bound.
Yeah, okay, we're going, okay, yeah. Can I use L? I is too loaded for me.
Okay.
I can't, oh, no, I'm not gonna take away your power. No, okay.
It just I'm not you.
What's that?
You can use whatever you want.
Okay,
It
thanks.
feels wrong.
I just don't, I wanna hear why it's loaded for you later, I guess.
Because of complex
Yeah, that's a
analysis.
number.
I just spent a whole semester
Yeah.
doing calculus with I.
I was our best friend for,
Yeah.
like,
That was just too much. A bit of an overbearing best friend.
You know what?
Use L.
Fuck it.
oh my God.
I can deal.
You can use a capital I.
If this is the worst thing that happens to me today, then I've got a hell of a good life. So, okay, so we're gonna assume I is an upper bound, or a lower bound, right? So check it out, Anna. I'm just kind of flipping the tails on that definition. because we assumed upper bound, now we're gonna assume lower bound. So we're gonna say I is the infimum of A if and only if, and let's enter this for every epsilon greater than 0. Draw a damn picture, right? And here's A. We'll make A look something like this. And I want I to be this least upper bound, excuse me, greatest lower bound, like that. So which way do I have to worry about spilling, left or right? To the right. So what am I going to do here? Noah, come on, you tell me. You're the creator of our symbology here.
Then I is the infimum I equals inf A, if and only if for all epsilon greater than 0 there exists an A and A such that I plus epsilon is greater than A.
I love it. In other words, this is as close as I can get if no matter how tiny the amount I jump right is, so there's my little plus epsilon, there's going to be some A inside there. Something from A has to be inside it. Because if there wasn't, I sure did a pretty bad job of picking the greatest lower bound. I've got a new candidate, might as well move it up to S plus epsilon at least. So, beautiful. And then the proof proceeds in a very similar way. Does that make sense, Anna?
Yeah, I was trying to flip it, and that's why I was thinking of, y must have been an element to the left of.
Exactly. Then you were thinking right. That's great. Outstanding. All right, friends. Week 1, real analysis. Good job. Yeah, we'll come back and use this thing on next Wednesday. We're off on Monday already. Strangely. Yeah.
Okay.
That's MLK.
It's MLK.
Yeah, it's MLK.
Yeah. I don't know if it's better to have, like, the first
Yeah.
week have one on Monday, or
You
have
don't have to see how
the
I want to like, you figured it out.
Okay, which was
Yeah,
the game?
it's
I'm
like-
sorry.
So
I don't know.
proof is pretty much another.
Because I'm like, okay, I got my
Oh,
schedule set.
oh,
and then
okay.
I'm
So
just kidding.
I figured out for say
But now those
one of them
professors always
is greater
end
than
up
epsilon
being,
than the other, and I'm taking the difference.
it was